in soft robotics. It all started with the McKibben actuators in 1961 and went up to the now autonomously swimming soft robot in the Mariana Trench this year. And today we're going to have a small workshop on the field's past and future, and we have a few really interesting talks that we're going to see. But to start with, I would please you all to ask you, please turn off your microphone, your camera that you don't need. For questions, use the chat. And for further discussions, we have a Discord channel that will be open throughout the whole conference and will be also staying live and open after the conference so that we can network there and get into contact with each other. And today we're actually going to have a few quite interesting talks. The first will be from Robert Shepard, who's going to give a plenary talk about the field's past, which will be followed by Muhammad Hussein, who's going to tell us how to make the soft robots move. And then we have a talk by Marc Demelier answering the question how to make soft robots actually sense. Then we will see a talk before the break by Oliver Pekin about how to build or produce the soft robots today. And after the break, we will have a presentation by Adam Stokes, and he will answer the question how to make soft robots think. And we're going to close this session today with a talk by Connor Welch, who's going to tell us something about how to educate using soft robots. And we will have a plenary discussion at the end. And here I would just like to shortly highlight to you the questions, the main questions that we want to answer with our workshop here and also in the plenary discussion. So what's next in the field of soft robotics? Where will there be still pneumatic actuation, or will the field be actually shifting purely to electrically driven systems? What will be the challenges for the next 5 years, and where will be the field actually in 10 years? And hopefully we see a bit about that during this session today, and we can answer these questions and discuss actually these questions today with you all.
Hi.
Hi.
How are you? Good to see you.
How are you? So if you want to test your screen share actually, and then we can start your talk in 4 minutes.
Yes. Hold on. Let me see if I can share my screen. Okay. You can see my screen, correct?
Yes.
Okay. The reason that you might see that it's my daughter's name, Zunaifa, 8th grader.
Okay, no problem.
So don't get confused.
No problem.
Okay.
Perfect.
I just would like to see something also. Let me see. Okay. And you see this YouTube screen, right?
Yes, and if you want to have sound, you need to check the little box on the lower left corner when you start screen sharing.
Right.
But if you
no, I don't need to actually share the sound from the presentation or anything like that. I'm fine. I just need to make sure that you can hear me clearly.
Yes, we hear you perfectly.
Okay, very good. So I think we have still 3 minutes, and then there will be 20 minutes.
Yes, so 15 and 5 minutes of discussion, right?
Okay, no problem.
Perfect.
Thank you.
You're welcome.
I'm going to mute myself for now, okay?
Okay. So let's start with our first speaker of the day in our first session, who's going to talk and give us an idea on how to make soft robots move. And I'm happy to welcome Muhammad Hussain, who is a professor of EECS in UC Berkeley and was a founding professor on the electric and computer engineering at KAUST. And now this is your floor, Muhammad, and welcome.
Thank you. You can hear me clearly, right?
Yes.
Okay, very good. Welcome, everyone. I'm connecting you from Bangladesh at the moment and I'm going to fly out for San Francisco in less than 12 hours. So it's kind of like, rush moment for me, but I'm very happy to be here because I would like to learn a lot about this robotics. And I do believe that there is a lot can actually be done. So here is the perspective that I would like to first present. So increasingly, we are living in a world where the computers are not only used as for computing, they are basically now being integrated into most of the things that we know of. And as we go forward, that we know that there will be more and more biology integration. And that's where we see that Internet of Things, as well as Internet of Everything. So that means that requires increased demand for hyper integration. So now there are two things are happening at the moment. So essentially that there is data management, and then there is this data collection and data-based decision execution. So we are very much familiar with data management in context of the computing, because we know that we need to have high performance, speedy computing, energy efficient means low power computing, and we would like to carry them portable. So it means that they have to be area savvy, as well as every year we would like to see that we are getting the best for our bucks. So that's the cost efficiency. Now, there is also that over the decade, we have seen that these computers, that they can communicate with each other. Now, the question is that in the Internet of Things or Internet of Everything, what we are doing is essentially we are integrating sensors so that we can collect the data from the surrounding environment or wherever we would like to have them. And then this computing is going to actually analyze the data, and then they will be able to make certain decisions. And those decisions will be executed through the actuators part. And that's where exactly I see the robotics will be the very handy one. Now, we do see that the robotics as that the traditional one, in the sense of that the robotics which have been used in manufacturing. We are seeing more and more the prosthetic hands. We see when I was a young kid, I used to watch like Robocops, those kind of things. But more importantly, right now, we are seeing that the rise of that unmanned vehicle, whether you can say the self-driven car, you call it something else. And then increasingly, we are seeing also something which is the soft robotics. And that's essentially because we have seen the emergence of interesting materials which are responsive to certain stimuli. But we do recognize that there are a certain kind of material innovation and integration is already progressing. The question is that how we can actually integrate more and more electronics to them to basically control their movement, that what we want them to do. How they can be more precise. And that's exactly where my background might actually be fitting in, and which is essentially how to build electronic systems. Now, as we said that these robotics are going to be part of the Internet of Things and Internet of Everything, that it means that we also see that we would like to know that if there is a way that the different kind of chipsets, those electronics, they can assemble themselves and they can actually become on-demand integrated system Today, if we would like to build a system, then there are different ways to do it. And I will be showing that. So let's go and see. So there are two ways that today we would like to do it. So one is that we use different chips. So basically we have different kind of materials, and then we are building all these electronics on those kind of material system. And then we are calling them the system on chip. This is driven by the Moore's law. So where performance, power, and area, these are the advantages, but it requires a single substrate, and it's very difficult to use one certain kind of material, which might be good for computing, but may not be good for sensing or energy harvesting. There is another technology which is very popular, that you see that those green printed circuit board, where we have different kind of chips. Those are the black one with the pins, and then we integrate them, and those become the system in package technology. They can integrate heterogeneous ICs with added functionalities, and they're the mainstream, but they actually use the bulky printed circuit board. There are some flexible printed circuit board, but they are limited in flexibility. What I envision as a part of this, recently our Congress, US Congress has passed the CHIPS Act, where we would like to see a more growth in the semiconductor manufacturing. What I would like to see that if these different kind of electronics, they can assemble themselves and can build a certain kind of a system. So as an example, some of our colleagues in MIT, they posted this video from MIT Media Lab that you can see here. So essentially, these are the cubes. These cubes, they're basically that moving, and then like depending on how you have programmed them, then they are getting into different kind of shapes, and then they're causing the having this kind of the sizing. And so it means that we can actually build different shapes of material or integrated electronic system. Now, what you're seeing here, that they are pretty large. And why is that? Because they have been using the traditional integrated circuits or ICs. So they basically have inside these the cubelets, they essentially have the PCB-based electronics, and then they are working. But in my case, I would like to actually see that we go beyond that, and where these electronics that in the core, that the chiplets, they can basically assemble themselves. So we are essentially collaborating with them. Also, we're working with the Berkeley groups who actually work on this robotics. So I will be focusing on the what kind of electronics and they can assemble themselves. So we do recognize that there are rigid and flexible PCBs available, which are they have limited flexibility. There are stress fractures. These are from Samsung. Samsung actually showed that you can have small printed circuit boards, which are very thin. And then there are these kind of the conductors that they are going through like a backbone, and then we can essentially assemble them. So basically this is part of the origami and kirigami. But in our case, what I thought is that look at us, right? So what we have is essentially most of our sensing organs, they are basically outside. Obviously our tongue, which is inside, but our ear, our eyes, like our nose, those are outside. Our tactile, the touch, the temperature, the pressure, right? So those are essentially skin, those are outside. But at the same time, our brain, our memory and logic part is inside, right? So that actually inspired me to think in a different way, that if we can use the substrate, the electronic material that we use today, and we use only one side of it to build the devices, why we are not using the other side exactly the way that I just showed? So what it means that we are building electronics, which essentially where the sensors, the energy harvesters, the antennas, they are outside. Here are the antennas, here are the solar cell, here are the different kind of sensors. But all the data management circuitries, the ICs, the battery, they are basically inside, exactly like our body. So what are the key characteristics? We are using the thin film based components. We are using the both sides. So it's essentially area efficient. It also is making them cost effective in the sense because we are not using different substrates. It is allowing us to actually mix and match because this can be based on certain kind of material. This can be based on 3-5 material, just as an example. And these can actually be made with silicon, which is essentially 90% of the electronics are made today. So I can essentially do heterogeneous integration of materials and devices. And it basically combines both the system on chip as well as the system in package, but they're essentially completely a standalone system. So here is, you can see the actual image of these kind of systems where we do have all the sensors are outside, and then there are the inside are going to be those, the data management circuitry. So now how we are doing it, essentially, we have the wafers, we are building the devices, we upside down, we build other kind of devices. They're connected through silicon via, then we dice them, and then we are packaging them, okay? So as an example, as I mentioned, that this is an example of that germanium-based substrates. This is gallium antimonide, and then this is silicon. And we are calling these multidimensional integrated circuits because unlike like, that 3D where we are having one on top of another, the silicon-based ICs, here we can have different kind of ICs and we can actually control different shape because the cubicle is not only the one kind of shape. I will show you that we can make pyramid and other hexagon and octagon, different kind of shapes. So we have taken them because we expect them to act like as a robotic cubicle piece. So mechanical ruggedness. And so we did the shock testing, like from 15-meter height, we did the 10 drops and shock is absorbed by the PDMS or the polymer-based encapsulation, which is essentially mechanically robust. So what happens is, you can see here that there are these kind of UAVs. They can basically, we took them we basically fly them, and then there was those were the ICs, and we just drop them off. And here, this is from the really high, tall buildings, and then we are seeing that they can actually absorb the shock. So here is an example of this standalone system. So essentially, basically it has the temperature sensor. It also has an LED and microcontroller and battery. The way that it happens, that when the temperature is above a threshold, which we set at 38 degrees Celsius, the microcontroller turns on the LED. So you can see that every time that whenever the temperature went above the 30 degrees Celsius, you can see that the LED was basically on. So now, if we move forward, then here you can see, that this is essentially that it looks like what is the inside and how when we are covering them. But the overall is, if you look at that, compare that video that you saw, that the video had the cubes, which were essentially 4 centimeter. But now we are having 2 centimeter, 1.5, 1 centimeter, 8 millimeter. And this is a medical pill, a capsule. Then we have the 5 millimeter and 3 millimeter. So essentially what we would like to say that these are scalable. So ultimately what we are looking at, that they are a standalone system and they will be able to move. And then they are going to, like Lego block, they are going to mix and match with each other to create a far more hyperactive integrated system on demand, where we can actually drop them off and they can assemble and reassemble themselves to have the systems which are on-demand manufacturing, and we don't need to actually be there to create a complex system, essentially. So from an scalability, I would like to also show that the MDIC, or the multidimensional IC that we just showed, the stacking reduces the footprint by a factor of 12 compared to the traditional PCB, which is the ideal case. Just as an example, that if I use the traditional system in package, then I will need to actually build a system. All these different components, they have to be placed side by side monolithically on like in lateral fashion. But the way that we showed in this case, we can basically the cubic MDIC, which essentially can basically be far less area consumption So it's area smart, as well as because we are using the two sides of the substrate. So we have more the advantage in context of the cost. Now, I just said that there can be different kind of shapes. That's also something very interesting, because as I showed a few slides back, that they can be folded in also different ways. So not only that multiple of them are going to build a system, but they themselves can actually assume different kind of shapes to themselves. So here is an example of a completely like in a Buckeye ball or something like that. The more the areas, it means that we can have different kind of sensors, as well as different like on the energy harvesting capabilities and the antennas. And this is like on the 2 centimeter side, and this is like a pyramid shape. So there are different things are possible. So if I compare what we showed from this, and we compared them with the system on chip and system in package, the heterogeneous integration perspective, that we have more capability to do heterogeneous integration. Our density is going to be high, same is like in the system on chip. Yield is going to be also high, like system in package. Form factor is going to be medium, because the system on chip, the 3D IC, they can actually go at least like, from thickness perspective, they are going to be thinner than what we showed. But from multifunctionality perspective, that they basically are going to be far more higher. So essentially, it has pretty much what you see from today's perspective, an ideal version. Obviously, going forward, maybe a decade from now, it's going to be something different. So here is something we showed an example of these water sensors on other outer side and solar cell on the upper side, and air sensors and encapsulation for floating capability. So basically what is happening here, as you can see, like on the, I'm not sure the video is on or not. So essentially when we dropped it off, it basically, the way that it did is it had a certain kind of weight, the mass, and it essentially allows it to take the sensing side, immersing into the water. And it's getting water, the pH, the temperature, as well as the other kind of chemical concentration from this kind of water. And it's very much important for the water security. What happens is the way that we have designed it, the sensor side, whenever it goes on the bottom, so it's immersing in the water, the solar cell side is always looking at like on the far face, like on the frontal. So it can get the sunlight to essentially have the energy harvested. And then there is this, on the side, there is this antenna. So real-time water monitoring, they were a result. So essentially what I would like to say, that when we look at the robotics or the soft robotics, then we see that it's more and more engineering of the nature. We are learning from nature, and then we are mimicking that through engineering. And we do believe that the multidimensional IC, this new design concept for the integrated circuits, the electronics, that they will be able to be part of this journey and to assemble themselves, as well as multiple of them to assemble themselves to have and far more complex integrated systems on demand. We are using bifacial usage of the substrate, small footprint, heterogeneous integration. We are taking it to a different level. It combines both the benefits of system on chip and system in package, and it all uses the traditional complementary metal oxide semiconductor, or the CMOS technology today. And they're scalable in size and shape and volume. And so that's where I will conclude my talk. And I would like to actually acknowledge my past and present group members, my collaborators. In this work was initially supported by KAUST, and currently it's going to be supported by the US DOD. And the industry sponsored was Lockheed Martin and Saudi Aramco. Thank you so much.
Thank you for this quite interesting talk. We have now 1 minute left for a quick question. And just my question is, can they actually now move themselves, or is that a more static system here?
From the movement perspective, what we have done as of today, what we saw that if we have like, the magnetic, the ball, whenever, so essentially, let's say that we are talking about a cube. So a cube has inside 6 sides. So whenever we are energizing a certain side, so that magnetic ball is essentially getting attracted toward that. And that way, because they're lightweight, so they can actually keep moving themselves. But I do believe that there are other certain ways, and these also can be perfected so that they can flip, they can start flipping on each other. Okay?
Okay, cool.
Thank you.
Thank you. And thank you very much for your nice talk.
Thank you.
To keep in time, we will now go on to Marc Demelier. And Muhammad, I hope you will catch your flight and hopefully also be able to stay for the plenary talk, plenary discussion afterwards.
Okay, so, we'll see. Thank you so much. Okay,
you're welcome,
okay,
and
thanks.
you can post questions to Muhammad also in our Discord channel. And now we're going on to Marc Demelier, who's going to give us a short inspiration on how to make soft robots sense. And Marc is professor of nature-inspired manufacturing and microsystems at Heriot-Watt University in Edinburgh, Scotland, and he does a lot of things. And I think he can now present those to you quite well. And Marc, the floor is yours.
Thank you very much, Volker. Can you hear me? Can you see the screen? Is that no problem?
I can see both, yes. Perfect.
Okay, perfect. So I give a very short overview of what I believe sensor could be helping. I noticed that for the plenary session yesterday, Olga talked a lot about sensor for seeing. So I will skip that a little bit. I will look more at the tactile sensors and explain also some of the work we have been doing for that. Well, apparently we have 5 senses. I don't know if you can see what they are, so it's a little bit of a quiz show here. The first one will be the sight. I think that's an obvious one here. The other one would be the hearing. The one would be the taste. If you look at the glass gives it away, the person that is holding the glass. The other one would be the smell, with the meaning of the rose, and the last one would be the touch. Actually, this painting being from the Netherlands, for those of you who are familiar with art history, there is also much deeper meaning for all these actions that these people are doing in the portrait. But I don't think that's the topic of this talk today, so I will skip that. So we have 5 senses apparently, and we also have 5 sensory organs again apparently. We have the ear, we have the tongue, the nose, the skin, and the eye itself. I say apparently because there's still a lot of questions. Some are being elucidated. I don't know if you have been familiar with the recent work done in Nature concerning magnetoreception of pigeons, where there are increasing body of evidence that you have magnetoreceptor in the brain that provide you with an idea of for the pigeon to align themselves with the magnetic field of the Earth. So, and that is, you will not find that in the sensory organ. So I think there is still much to be discovered, but this is a conventional wisdom at the moment, so I stick to that. It's always possible when you look at a sensory system to describe a functional schematic. So you will start with the sensor itself, and the sensor is rather dumb, can be rather dumb by itself. And the sensor will be stimulated, but you will have some sort of data receiver, either coming from the sensor itself or something which is directly activating the sensor for information. And you need to build an interface in order to get to your cognitive processing system, that is your brain. And then following that sensor, you might decide to have some actuation, or you might get some information which will be going to your brain. And then this is a reaction that you're going to give to the system. So I'm trying to describe this functional schematic in order to maintain that sensory system. You need some energy of some form, and there was a very nice work by Robert mentioning the combustion and other aspects of energy that you need. But you need also to be able to procure that energy in one way or another, procure it to the sensor, and also to store it and to manage it. And all that is underlined by a kind of knowledge base of firmware, as if I take an engineering viewpoint about what that sensory system should be. And in order to select whether or not the information is relevant to the cognitive processing system, you will have some criteria that you will be having in order to regulate all that and to have relevant information. And having that technology mapping, then you can design really the technology you want to map into that. Some old technologies, some 20th century semiconductor-based technologies, and you have more recent technologies that you can map into that. But this is very much a sensory view, a functional and technological mapping of what I would believe a sensory system would look like. And then you can start also, it doesn't mean that because you have a functional system that this functional system is cannot be broken into different parts. You know, you can have parts which are in one part of the body and one part which is actually completely outside the body. By body, I mean the robotic system you're going to have, or it can be fully embedded into it. So it allows you to have some reflection, and then you can build this kind of workflow that Robert was mentioning, which is quite interesting, in order to make sense of the various parts. So that is something you would want to use maybe during your work. And I said I would look at the example of the tactile sensor, and there was a very nice review by VP Namoli and colleagues just a couple of years ago, and it was rather illuminating. So they were looking at the different tactile sensor, and they were breaking down the actual taxonomy of the sensor according to the structural design, the functional design, and the actual sensory system as well. And I think it's fair to say that the work that has been done mostly at the moment, it has been very much on the structural design, because we are engineers, we're familiar with that, and the advanced sensory system as well, in order to create a system, in order to get it into your robotic system. But there's still very little work done on the nature-inspired, the functional design as such, in my view. And this is where I would think that synthetic biology, which is called now engineering biology, and also material science could provide a lot of activity. And these are bodies of some métier, I would say it in French, which would be quite useful for the biorobotics community, in my view, the self-robotics community. So looking more specifically as a nature-inspired structural design, to give you some aspect of the work, I will not talk about the gecko because that has been talked many times already, and we had already a talk by Mark yesterday concerning two of the structures. You know, the gecko has three levels of structure. I'll be talking about two of them, which are being replicated very successfully. So I'm going to talk about the various other structures. The one is the kind of whisker aspect of it. And what you have with this kind of whisker, you can look actually at the velocity of a gas, for example, passing above this hemisphere. But I look at it now from an engineering point of view, from a manufacturing point of view. I mean, great work, obviously, that has been done. But it all depends on the manufacturability of these electronic whiskers. There seems to be, in my view, sensors which would be quite difficult to replicate on a mass manufacturing point of view. They tend to be also quite fragile, in my view. And so I'm a bit worried about the robustness in real life application. Don't get me wrong, I do not want to belittle that work. It's great work, but I'm trying to look at, would that be working in real life application? Would that be working in thousands if we were to use that for biorobotic systems? Another example is the actual sensor based on cracks, and so you can see the small arrow here. There is a cracks. If you were looking at as a broader picture of one of the legs of the spider, you have this kind of tracks, and what you are relying about is you're relying on actually looking at the variation of the voltage as a consequence of this crack, which will give you an idea of the movement. So you rely in a way of an imperfection, a voluntary imperfection of the actual system in order to detect basically getting some haptic feedback. And again, it depends on the manufacturability of the crack-based sensors. So so that is one aspect of it. So Dr. Kang created a very nice work based on a carbon nanotube, if I'm not mistaken, or graphene. And you want to look at the reliability in real life application. So how many times those cracks can be used and how many cycles those cracks can be used reliably, and you get reproducible results. And this is some work I've been doing on instead of using cracks, looking at this kind of wrinkled metal layer, which has been surviving 1,000 cycles with bending of 180 degrees without any deformation whatsoever. I'm going to explain that a bit more here. And then you have this other example of pressure sensors, this time based on the porous structure of a sponge here. And you have the very classic system that you find where you have a kind of porous structure which is embedded into ITO film. And you have this very classic picture concerning the pressure on one side and the actual output response on the other side. And you have this kind of two curves, which are very classic of nanostructure layers you will find, for example, in a piezocapacitive sensor or other type of sensor. This case being a piezocapacitive sensor. But it doesn't need to be in the form of a sponge. I mean, any nanostructure would do the work. I think what you're looking for is a way of manufacturing easily. This is the key, really. But again, very nice work, which has been done. So if I, looking at all this example, and I've been spending a bit of time for that talk, is, over and above the accuracy, you need the specificity, the selectivity, and so on and so forth. You will want to know what are the ideal specification for your biorobotic sensor. Well, first of all, you would like to have a decentralized control if you can. That is, be able to have a sensor for which the intelligence is very nearby or even embedded, because that's something that we have, for example, in our body. You want to have something which is also self-powered and also self-interrogated. So by that, you will want to have something at least for which the power doesn't come from the mains in a way, something which is very close by as well. You want something which is robust and reliable, and I mentioned so some of the sensors presented might not be the case. You want to have some sort that we call built-in self-test, which is quite common in microsystem in general and also in electronics. So the ability basically to auto-calibrate itself, but also to look at failures, which could happen, and allow your sensor to fail gracefully when it is close to the lifetime, to the end of its life. But also something which is a built-in self-repair. And again, Robert mentioned this kind of self-healing material. Again, we have that which is happening just now in microsystem, in MEMS. It's been there a little while in electronics, not as much as we would like to, but it's something I think we should have for these sensors. And the ability also to have multimodal sensing modality in order to reduce the number of interfaces. So if you could sense more than one thing, more than one measurement, I think that would be great. And that will help you actually for the built-in self-test and the built-in self-repair. So you have 2 or 3 things for the price of one. So that's something we have been working quite a lot concerning multifunctionality sensor as a way, as a solution to BIS and to BIS. And you would like to have a fast time response, but that depends on the application. Chemical sensing, for example, it is not necessarily fast, but it can be quite selective, quite specific. And if the application required only a second of response time, why not? And ideally, you would like something which is relatively non-invasive and also conformal. So you can conform to any surfaces that your soft robotic system has. And finally, and I think it's quite important in my view, it has to be based on manufacturing process which is integrative. By integrative, it's a manufacturing process which lends itself to have other manufacturing process to be built upon. This is what I mean by integrative. That is, it allows a flow of manufacturing process to be happening without too much modification of the tools, etc. So I'll give you a little bit of my commercial break here. So a kind of haptic feedback sensor we have been doing ourselves, which is self-powered, self-interrogated, which can be tuned for different applications depending on the pressure you want to measure. And it's also fully flexible. It's a capacitive pressure sensor. It does a normal force, a specific version, but it can be extending to shear force. So you have this multi-directionality of the force. And it is based on what I will call a 20th century technology. The reason behind it is it allows me to piggyback on the multi-billion pounds of investment that exists, and also to accelerate the actual take-up of this kind of sensor. So to give you an idea about the pressure, the complex of the pressure, remember that the sound wave will be typically between 1 to 10 Pascal. The breath will be between 100 and 1 kilopascal. What we are interested in is probably pulse pressure and gentle touch, and that would be in the region between 1 to 10 kilopascal and 10 kilopascal to 100 kilopascal roughly. So this is the kind of pressure we are trying to look at. So coming back to the haptic feedback sensor I have, the one I manufacture is very simple. It's layers of PDMS with a nanostructure in the middle and just 2 coils, base of metal. And the way it works, it's basically an RLC sensor. So as soon as you interrogate that sensor, you are pouring the sensor and you rely on the inductive coupling of that sensor. So it's a very simple system. And what you can do, you can have the powering system be embedding, for example, inside the finger, and the actual radar antenna might be the object you want to detect. So you rely on a change of pressure, which will give you a change of capacitance, and therefore a change of frequency because you have a resonance structure. And by looking at this change of frequency, you can deduct again the applied pressure. So this is an example where you see that shift of frequency depending on the coupling coefficient, which is a function of the distance between your sensor and your readout, as well as a function of the pressure. And when you have done that, you can see that's a shift of frequency happening, and it happens to be quite a reasonable linear expression of the actual pressure. And for an electronic engineer, having a linear measurement is actually good news. It simplifies tremendously the electronics. So the manufacturing process, and we've done that with colleagues, Dr. Phil Hans at the University of Edinburgh, it's a semiconductor manufacturing process, but it is a self-aligned one, which is also quite good. Most of the previous research rely on manufacturing the layers independently and then sticking them to one another. This is not the case. This is something which is completely, you build the system in one go. So you see a top view here of the top layer of the sensor, which has this nanostructure made of pillars. You can see clearly the actual foil, the actual coil, should I say, which is made of this kind of wrinkle layer that I explained. So if you look more carefully, you will see that wrinkled metal layer, and it is not based on a preset substrate. It is based on a different system. You rely, in fact, on thermodynamics. And as I said, we went to bend that layer 10,000 times with actually no cracks whatsoever for that crinkle layer. So it provides you a very good conduction. And the intermediate layer is a simple microstructural layer based of a truncated pyramid, which are called frustra, I was told. So a new Latin word for me to learn, which allows you to have this concentration point concerning the pressure, and therefore be very sensitive to pressure if you want to.
Mark, you're running a bit out of time.
Okay, so I go very quickly then. So we have a kind of manufacturing process here, which is provided here, which allows you to create many things. You'll be able to characterize that in the response range that you want for the touch. And we did some experiment to use in this kind of simple pressure cap. So, and that is to look at a medical application. And we've been able to detect, for example, the mechanical ventilation of a porcine of an animal model. This actual sensor is in the gut of the porcine, and we're able to detect the mechanical ventilation as well as the heartbeat. So there is other kind of sensors, unusual sensor you might want to look at, which are this kind of vertebrate vestibular system. And it's a very nice, interesting idea inspired from biology, which is, this work is still not done completely, but it allows you to detect basically the actual acceleration and of the actual head where you have that system. And it's something for you maybe to look at as a way of getting something slightly different from your classic accelerometer that you might want to do. So something based on fluidic system. So in summary, there's definitely a variety of sensing modality available from nature. The key is to map your specification with the characteristics of the sensor and to translate them into manufacturing relevant process. That's the key. But bear in mind that the sensor, all the sensor from nature are not necessarily the best to perform the task. You're not necessarily have the optimum sensors as in nature. Okay, that's me. Thank you very much, and apologies for having talk a little bit over my time.
No problem. We have time for one question. There was one in the chat, and it is a two-part question, I think, from James Drayson. I will just shoot the question. How does cognitive processing develop in the future to get sensory data to look more like the first-person experience?
Oh, that's not my field of specialism here. I will need to talk to James to try to understand what he means by that. I'm sorry, James. I will not be able to answer that.
For that, we actually have the also the break in a few minutes, and also we can use this Discord channel here, and there we can post these questions again. So with that, I would thank you very much, Mark, for your wonderful talk, and we see us again in the plenary discussion of the field's future. Now, I would like to welcome Oliver Pekin. I hope I say your name right, actually. He's an associate professor with INSA and iCube Laboratory in Strasbourg in France. And his research interests include medical robotics and mechanical mechatronic designs. And he will talk a bit to us about the question how to build and produce soft robots today. Oliver, the floor is yours.
Okay, hello everyone. So I will talk about manufacturing of soft robots in a particular context with a specific class of materials, polymers and elastomers. In fact, you can see my screen correctly?
Yes.
Okay. My presentation, I have trouble with, okay. It will be on manufacturing of soft robots, but this topic is embedded within a much wider landscape. And as you can see, when we are talking about soft robots, it can be seen as an evolution of robotics in general. And things are getting more and more complicated for designing and fabricating this kind of systems. So here you can see a list of different challenges or key issues that are only partly solved today for dealing with soft systems. So my talk will be only on today on materials mainly and fabrication methods. So among polymers, elastomers are specifically relevant for manufacturing soft robots. In fact, they have many desirable properties: high extensibility, high strength, high energy absorption, high resistance to fatigue. They can maintain flexible at low temperature. And another important point that they can be combined with other materials, either for reinforcement, otherwise to overmold other component. And this is a point which is specifically relevant for soft robotics. So manufacturing of soft robots is a challenging task because even if you restrict to the specific class of elastomers, the number of available nuances is very high. And this extremely vast range of materials can be processed by a very large number of manufacturing methods. Furthermore, these methods have different features that can be continuous or discontinuous processes, direct or indirect manufacturing methods. They can be adapted to unitary or prototype, otherwise for larger production batches. And depending on that, it will change sometimes a lot of things. And of course, the manufacturing methods are heavily dependent on the material properties. Parameters such as viscosity or curing parameters, as we are talking about polymers. These are some important parameters. There are also a strong interaction among material, process, and design. Parts with a given geometry and a material family will generally require specific processes for manufacturing. The final product properties result from the complex transformation that occur during the process on the input material. And that is the main reason why it's sometimes difficult to make a good prediction of what you get out the process. And the reason why we are doing a lot of trial and errors on this kind of process. Elastomers can be classified into two main categories: thermosetting elastomer, Tse, and these are the majority of elastomers used in engineering applications. Thermosets are melted and formed only once. These materials can go through an irreversible chemical reaction when processed, and they are finally set in their final shape. Example of that are EPDMs or rubber or silicone. And the other class of elastomer are the thermoplastic elastomers, which are increasing in number and use and also in type, because thermoplastics are materials that are capable of being molded when you add some heat. And this material can be recycled and it can be remelted and formed again several times. So this is advantageous, notably for recycling. Some example of such materials, Santopren, Ninja Flex, are a kind of materials that can be used in 3D printing. Apart this classification, one important feature for this elastomer are the mechanical properties are of top importance when you select a type of elastomer. There are three distinct features for the stress-strain behavior of elastomer. The first one is a large deformation response when you apply the load. Because this, when you apply this load, deformation can be large with a relatively low stress level. Rubber materials can deform easily, and this is a principal feature that is sought when selecting an elastomer for a specific application, and when you are doing a soft robot, for instance. Non-linearity is another feature of such material. When you consider the huge percent deformation, another important feature is the non-linearity of the stress-strain behavior. And this particular property also appear when you apply cyclic changes, in which you can see that time and history impact the response of the material. So if you take a rubber test piece, it will change its stress curve radically after a first loading. And if you continue to change, the behavior will continue to change. But after a sufficient number of cycles, a kind of equilibrium is found. You can find the equilibrium modulus for the system. And this is an example of effect that is difficult to be taken into account to predict the final behavior of the system. So TS and TP elastomer have specific transformation processes. After a phase of mixing, TSC compounds can be shaped while chemical reaction continue until the full setting of the crosslinks. The chemical reactions are initiated by heating. In contrast, for TPEs, processing involves heating pellets to convert them into a hot melt, and then shaping and cooling the hot melt to form the physical crosslink and to get the final part of the system. Here is an attempt for classifying some process parameters for these two types of elastomer. This picture shows some manufacturing method as a function of the process duration and the viscosity of the raw material. The processes corresponding to TS and TP appear in red and green, and there are more type of process for TS than for TP, although the offering for the latter is currently increasing with new machine, for instance. Some methods tend to be specific to a given material, for instance, liquid injection molding, but the elements that you can see at the bottom of the picture and the right part of the picture correspond more to industrial process. This industrial process does not really apply to building prototype system like a soft robot, but you can find interesting idea in this industrial method for fabricating soft robots. So some methods tend to be specific, and you can also see when you have just prototype to do, you can find the main class of 3D printing techniques that work with both low and medium viscosity, silicones or TPEs in filament for FDM 3D printers. From this set of techniques, I will now show two examples, one involving multi-material additive manufacturing, and the second with vacuum casting, which is a way of constructing soft systems using mold. So to start with multi-material additive manufacturing printers, they are of great interest because they can produce parts with different material properties. The machine we have used here is a Stratasys Connex 350 based on the polyjet technology. It can process a range of thermoset resins by photopolymerization and produce multiple digital materials. This technology allows a direct manufacturing of prototype with complex geometries that could not be produced by another manufacturing process. This manufacturing process also has a great apparent simplicity, but it has also important limitations. The first one maybe is the rather reduced range of materials. This is typically machine dependent, with generally only a fraction of the performance of materials available for injection molding or casting. This is an important limitation. As a material transformation is a complex process, the final properties are difficult to predict. And another point specific to the examples I will show later is that airtight or hollow systems remains rather difficult to obtain. So the system we have fabricated using this process was a soft pneumatic actuator produced with this multi-material machine. The general design goal for this application were to build elementary building blocks or units, each of them providing a small translation displacement or an angular contribution. Each unit forms a kind of deployable mechanism and based on a kind of origami or foldable or deployable structure. So the proposed architecture for the system is based on the inverted honeycomb pattern with two configurations of the same pattern. Allows for rotation, otherwise translation motion. And the objective was to fabricate this type of airtight articulated polyhedron. Here is the design system that we have done for this. With the central deployable part is monolithic, fabricated with rigid and soft materials. The closing of the units is done with two separate rigid plates. And here, in fact, the most difficult part we had to do was the flexible hinges to produce. And we had to take special care to design the geometry of the flexible hinges. This is the version with the rotational capability. In this kind of architecture, we have studied two types of hinges. The first one with stiffener and soft materials, and the second time only with soft materials. We conducted different tests on the system. And in fact, what we arrived at is when the system is operating, you can see ridges from the multi-material process with combined loadings. especially at the top of the closure caps. And if you push up the pressures, the system, in fact, fail with a pressure in the order of 40 kilopascal. In this case, the soft material produced by the machine has quite limited strength compared to what could be done with regular silicone if you are in the capacity to produce with silicone. So another experience we have conducted was to use another process, vacuum casting, which has different advantages. Advantages is the variety of the shapes and the resins that you can find on the market. In fact, it's a myriad of resins, so it complicates the choice, but you have very large choice. You can use this technique to overmold component. This is important, as I already said. Properties of final parts are predictable and can be easily repeated from one fabrication to another. The equipment is quite limited. You have just a vacuum pump and one oven to process the process using this method. So this is relatively low cost compared to the previous method. So of course, disadvantages are it is an indirect process that need some additional work. In fact, you need to design the mold, fabricate the mold itself, and in the fabrication of this mold, we have to take different there are different rules for designing, in fact, the element. First, you start by designing the part. The part should be designed with some rules. Some rules which are different in case of silicone or than for TPs, thermoplastics. You can have very thin walls, very fine details. It's possible. Fine wall thickness does not need to be uniform. You have to take care also about shrinkage. Draft angles are also desirable to ease the demolding of the part. And you have the regular rules that you use when you design plastic parts, in fact. Then the next thing to do is to design the mold. And what we have done here is a kind of, we have revisited the fabrication of a Pneumatic, a pneumatic network using a split mold. We have done this based on what is done on parts that are produced in mass production. And this type of element is very interesting to ease the removing of the molded part. We had a video that does not work here. Okay, it's no problem. When you are designing the mold, important elements is the position of the gate. This for the good feeling of the mold. And here you can see different elements, such as a good location for the different parts of the mold, a good clamping of the mold. And also an important point is the placement of vents to avoid air entrapment in the mold, to avoid bubbles in the system. For the choice of material, it's very important to make simulation to predict the behavior of the final system, and this can be reasonably be done when you use resins, silicon resins, as we have done. So the next step is the casting itself. So you have to mix the elements, apply some release agent on the mold surface to ease the extraction of the part, and then the cure of the part is completed within when you place the part in the part on the mold in the oven. So the curing phase is activated by heat. I'm sorry, this video doesn't work. Okay.
The right one did work, Oliver, but we're running a bit out of time right now.
Yes. So this was the animation. On the right, it works. In fact, we have made several pneumatic networks. One with a single air chamber, and the second one with dual chamber. The project behind this is to make a gripper that will be capable of doing dexterous manipulation. As I'm running out of time, I'm just arriving at the conclusion. As concluding remarks, I can see that the selection of adequate trio design material process is already a difficult task for single part, but it's even more complex for soft robots because they require lots of embedded features. Therefore, the production of soft robots does not seem to be feasible really with a simple and single process. Despite rapid advances in 3D printing technologies. Manufacturing of soft robots has not yet reached its full maturity. And as I already said, the current methods still rely widely on trial and error. So maybe some of the difficulty for fabricating soft robots is about the embedding of discrete component. This is a recurring demand in soft robotics. And to better predict the output results, simulation and also design tools need to be developed to overcome the difficulties for simulating discontinuous manufacturing processes of 3D printers typically. Simultaneously, fast-paced advances in the printing technology, the latest 3D printing with TPE start being available at reasonable cost, but not for all the models, of course. So in terms of perspectives, I think that learning and applying some rationale from the polymer industry, because some tools are already there, specifically for studying the rheology of polymers to simulate continuous transformation processes. The objectives will be to reduce the trial and error and better predict the end-use properties of soft robots. I think that a careful combination of manufacturing process, direct and indirect, with supporting simulation should help. And finally, maybe 3D printers with open architecture hardware and software would be of great interest for to better control process parameters. Okay, thank you. I'm a bit out of time. My apology.
No problem. Thank you very much, Oliver, for this nice talk and short overview about technologies to manufacture different soft robots. One question I have, and I find it quite interesting that you use the Stratas, is: did you ever think about really hinged, so really mechanical hinges? Because I saw now that you use the flexible version there for your pneumatic. Is it really tough to do that in a mechanical hinge there?
In fact, the difficulty for the Stratasys is that materials is not very consistent in properties. The properties vary in time. Mm-hmm. If you go 2 weeks later, in fact, your prototype has shrinked a lot, maybe. Okay. And it's not on the strength and the resistance. It's far less good as silicone that you could cast. But the difficulty for our system, for our pneumatic system, it's not so easy either to make a vacuum cast of an hybrid system. So I think that maybe a way would be to mix different approach. The one with 3D printing for instance, for the most rigid parts, and after that, overmolding the flexible elements using the vacuum casting.
It sounds quite interesting. Do you think also about using multi-material filament printers, where you could also, multi-head printers, because there are currently a few on the market with using multi-head and multi-tool printers? So they could add in actually a rubber printer, print head, or a print head for silicons there with syringes.
Yeah, I know that recently, or maybe 2 years or 3 years ago, for the first one, silicon printers exist, but it's the same process. It's a layer by layer production. Mm-hmm. And this is maybe the core problem, because it's far different from a continuous casting. Mm-hmm. Because when you process a material, during the process of material, you transform the material on the way. And if you constitute the part layer by layers, the issue is maybe the adherence properties that will not be the same as the same part that you have casted, for instance. Mm-hmm. It will be totally different, and it's rather difficult to simulate. In fact, to simulate what 3D printers actually do on the material for the final properties of the part. This is, I think, the most difficult problem for predicting the behavior of the final part.
Mm-hmm. Okay, thank you. And thank you very much for a nice talk. And I don't see any questions in the chat right now. So I would say thank you to all the speakers for the early morning session, can I say, because we have an afternoon in Germany right now, for the first session. And we now go into our break, and we will resume at 1600 UTC, so in around roughly 45 minutes. And to everyone, enjoy your break. So Adam, if you want, you can share your screen.
Sure, thanks, will do.
And while you're doing this, I will just shortly give you a highlight on Adam, because he's a deputy head of the Institute for Integrated Micro and Nano Systems at the University of Edinburgh. He's also the director of the Soft Systems Group, which is an interdisciplinary research laboratory which focuses on robotics, fluidics, and complexity. And he will today give us a talk about how we can make soft robots think towards soft systems, challenges, and opportunities in engineering with soft technologies.
So, can I just check that you can see my screen okay?
Yes, I can see your screen.
Okay, thanks for that. Okay, so first of all, thanks for the invitation. It's a pleasure to be speaking at this conference. I last spoke at this conference in 2016, and there's lots of things that have happened since then. So it's interesting to sort of take stock and see where we've got to with some of this stuff. So when I talked in the Robosoft meeting a while ago, I gave a bit of an overview of the field by using a sort of analogy from Greek mythology, and I think it's apt in the context of living machines. Here we've got two different systems. One of them is Talos, which is from the Bronze Age of men, created by Hephaestus out of metal, and essentially is an automaton. And then you've got man, created by Prometheus, and Athena breathed life into man. And this is sort of known as the golden age of men. And I think we're witnessing a similar sort of thing in soft robotics. They sort of move from automata and systems that are made from metals and plastics into systems which are much closer to living systems. And soft robotics is very much something which takes us along that line. So the talks that we've had so far are things about making robots move, making them sense, how to build them. I'm going to talk a little bit about how to make them think. An observation here is that all of these are subsystems of a whole soft system. Movement, sensing, thinking, they're all just typical classical subsystem architectures. And that's very much one of the ways that we look at the problems in my research group, is that we decompose complex systems into subsystems, and we can focus on making those subsystems work very well. So, this is an oft-used diagram showing the sort of evolution of robotics away from the traditional sort of architectures that you have for robots and towards things which were inspired by squid and octopus and things of that type. And in the talk, I'm just going to highlight a couple of things. We're going to talk about the fact that robots aren't complex. I'll talk about the fact that we need to be able to make smart materials as stable subsystems of a complex system, that we get intelligent materials from interactions in complex subsystems, and finally that soft is something which adds value to robotics. It's not something which is anthemic to it. In fact, it's something which I believe will be the future of robotics. So in my teaching, I teach in biology and electronics and chemistry. And in all of these areas, one of the things that we observe is that we end up looking at complex systems and trying to understand them using successive layers of abstraction and architecture and hierarchy to explain how these things work. And really, biology and electronics and chemistry are just ways of subdividing the world of things into different disciplines that we can try to understand. And we sort of do the same things in robotics. And one of the things that I really like is the parable of the watchmaker. And if you don't know this, then it's a really interesting parable to go and look up. There's not enough time to go into it just now, but basically it talks about the idea that in order to make stable systems, then there's a lot of merit in making stable subassemblies, and that making stable subassemblies allows you to make complex systems with fewer full system errors than if you just make a system out of a complexity of parts where you need the whole system to be assembled. Otherwise it won't be stable. And it sort of gives a bit of insight into the way that we build complex systems in robotics, but also the way that complex systems arise in nature through these stable subassemblies. If we take robotics as a whole, then you can look at the tension between classical robotics and soft robotics as this sort of diagram here looking at a 6-axis robot versus a octopus arm. And if you think about it from the point of view of useful work, both of these systems do the same job. They can pick something up and move it from one place to another place. And you can decompose it into a really simple way of looking at it in terms of translation and rotation matrices. You combine these together and this gives you basically the whole of kinematic-based robotics. These simple ways of thinking about translation and rotation and making up big matrices, applying inverse kinematics, etc. It gives you robotics, manipulation, and locomotion. And ultimately, what are robots useful for? Well, these sorts of robots, 6-axis systems, they perform a useful task, which is manipulation, as that top-level description of task. The point being that robotics as a whole is not complex, especially these sort of industrial type 6-axis robots. They can look complicated, but actually the decomposition of it is that they're not complex at all. An interesting thing, if you continue the analogy of looking at all of the possible two-dimensional transformations, is that the opportunity in soft robotics research is around the sort of scaling and shearing matrices. And predominantly all of the work that we've looked at has been around the scaling matrix. And why is that an interesting way to look at it? Well, it's interesting because one of the things that scaling gives you is this idea of dilation. And I think that that dilation is really about looking at how we can interface or interact with our soft systems. And so, the reason why that's important is because it gives us this question, which is often overlooked, which is, what do we actually want soft systems to do? What do we want soft robots for? And I would argue that one of the major answers to that is interaction. The design of systems that brings in soft materials, living tissues, etc., looking at sort of softness overall, is all about design for interaction. So we can look at a couple of examples of this, and Rob showed some of this briefly earlier on about the robot that was made now 10 years ago, which uses this idea of scaling. And there's two things going on with this robot. One of them is simply, a dilation matrix of, in 2 dimensions. You can imagine a circle going from being small to being large. That's now in 3 dimensions, and we pin it in one way, so it gives a little bit of complexity. And then we add in, 5 of these actuators to give us a robot that's got all this multifunctionality that Rob was talking about before, where the system is both the actuator and the stable assembly. And you can use the same sort of approach to look at a number of other robotic systems that we've built, things which are able to bend. We can combine these stable sub-assemblies to make robots that have these really simple sub-architectures that then end up becoming more and more and more complex with the way that we build up the systems. And really what this is about the design for engineering, making soft systems engineerable through the sort of intelligent design of the sub-assemblies that we can combine together. Why is all of this important in the context of how to make robots think? Well, it sort of comes down to this idea of thinking about the embodiment of systems. So if you take the argument that all of the robotic systems that we've made in soft robotics, certainly in my group and from a number of other groups, they build upon this idea of stacking together simple sub-assemblies to make more and more complex overall systems. And it brings in this sort of discussion about control and about how you actually control the system. And Rob, again, talked about this earlier on about the sort of onboarding or offboarding of control. One of the things that you observe with the offboarded control, which is predominant in all of these systems here, is that you've got a simple one-to-one mapping of control lines with the number of actuators. And it brings into the force a question about how do you control systems, how do you make them more complex without ending up with this sort of burdensome tether bundle. And it's a problem we've been looking at for a long time. And the answer really comes down to looking at fluidic logic. And you've seen this in things like the Octobot, and there's a number of papers that are coming out now around this idea of how you onboard some of the control and physically build the robot controller with the same fabric that you use to build the body and the actuators. And that's a really interesting sort of move towards systems integration. And it sort of puts in mind the sort of idea of how you do systems development. So a lot of the systems that we've seen in the past have been about taking a favored actuation technology, integrating them up to build a system. So simply stacking of these things. And in a systems engineering model, by contrast, what you do is you start with requirements, you work back down to the component level, and then you build back up to the system. And this sort of speaks to the maturity of the field that we're starting to have these sorts of conversations now. So one of the things that we've been looking at a lot with that in mind is looking at a task-based view of what you want robots to do, and then being able to look at how you both design the controller for the robot at the same time as choosing the most appropriate actuator. And one of the ways that we've been doing this is by looking at energy-based analysis. And this allows us to identify areas of loss. It allows us to look at how we can get regeneration and how we can choose actuators that are the right actuators for the task. So I don't have enough time in this talk to go into this in a lot of detail, but there's a number of papers about this, and I'd be very happy to talk about it in questions. But basically, we can model our soft robotic systems in terms of the sort of energy source to energy sink and the areas where they store energy capacitively or inductively and where they lose energy through resistive losses. And you can do this across all domains. So it's not just electrical, you can do this pneumatically, hydraulically, chemically, whatever. And so we've got a paper that's just about to come out in Advanced Intelligent Systems, where we go through lots of common actuators that are used in soft robotics, and we decompose them into understanding how energy flows through them, how energy is transduced, and how it's lost. So we look at new nets, we look at thermal actuators, we look at dielectric actuators, we look at piano Hazel actuators. And basically what the reason for doing all of this is that it allows you to understand something about the control of the system, how, in the context of making soft robotics think, then this idea of being able to look at energy flow really sort of starts to get to this point about the intersection between the brain and the body, the sort of embodiment of the system. And in that sort of context, then a body model where we can model the dynamics of the system really gives robots something to think about and gives us a way of being able to think about how we design an appropriate controller for them. So again, there's a whole talk in here, but one of the things that we've been doing is looking at examples of high levels of system integration, which you see in electronics, and trying to borrow that narrative to do this in fluidics. So we look at component level. So we look at fluidic transistors, and there's a number of different architectures that we've been playing with and other people are playing with for how you physically sort of gate the movement of gas from one place to another or fluid. And within this, then you can start to think about how you apply that complexity on top of it that allowed us to do what we did in electronics in fluidics. So we've built systems that use combinational logic to be able to make robots that can walk, with sequential logic, so now we can make robots in the same fabric as we build the actuators and the body, but they have a memory state to them, so they can understand something about state, which gives you ways of being able to embed history and algorithms into the system. And the point really is that control is a really essential subsystem for robotics. And in order to be able to make really useful robotic tools, then they need to have a control system. And that control system needs to be of the same order of complexity as the body itself. So the energy-based modeling allows us to look at how we model energy flows and how we look at interaction. And the control system allows us to sort of design the intended behavior to respond to the environment and to think about task, right? So one of the ways that we're doing this is that we're applying a lot of complexity to our systems by putting on top of it a fluidic hardware description language, which again just sort of borrows from this architecture that we see in electronics. It's a bit more complex in fluidics. There's a lot more physics going on with it. There's a lot more tests that needs to be done. But really, we're trying to take a lot of the tacit knowledge that people have from making soft robotic systems, and specifically the control architectures, and being able to put that into a bundle of tools that enable you to design complex architectures and complex controllers. And the reason for doing it is to try and hide some of that complexity and embed it in the body of the system, as opposed to having everything as off-board control, which really sort of limits the use cases where you can use your soft robotic systems. The other thing that's interesting about that way of thinking about stuff is that we, at the last Living Machines that I talked at in 2016, we were talking about this project, the Minimal project, which was looking at how we can learn from things like maggots. So in this case, these are Drosophila larvae, and use that as a way of understanding how they function, both to inform the neuroscience, but also to understand something about how we can use those architectures to make novel types of robots that can perform autonomous tasks like navigation. And these guys are really interesting. They can dig and they can do all sorts of things. And we really sort of got interested in this idea of how you can bridge this biotic-abiotic divide, where you can sort of bring in microelectrodes and cells and build these sort of synbio robots. And there's a number of people who are in this space now who are doing some really, really, really good work. But there's just some observations which I think are really interesting, because one of the things going into this project was trying to understand how do Drosophila larvae compute and think with such a small number of neurons in the brain. And Jane, who is a PhD student in the group, and with Barbara Webb, did some really, really interesting work looking at the neuromechanics of the Drosophila larvae. And the reason why I think this is really interesting is because it challenged the assumptions in the field. And by building up a model, which was not just a controller and not just a body, but actually was a sort of full neuromechanical model, then one of the things that Jane was able to do was to look at the fact that if you really sort of get into the nuts and bolts of what's going on in the Drosophila larva, then you can start to think about a different neuromechanical model of chemotaxis, which doesn't rely upon learning per se, but actually looks at the way in which motor neurons can be silenced by olfactory systems, which changes viscosity, which can bias the way in which the maggot moves, which then ends up making the maggot seem a lot more like a Breitenberg vehicle than like a sort of, sentient organism by itself, which I think is a really interesting insight about the sort of stable subassemblies and also the sort of the bridge between systems that are alive, systems that aren't alive, and what control looks like in biological systems versus abiological systems. And I think there's a lot of synergy there that's really going to be an interesting thing to explore in the context of how you make responsive, intelligent robotic systems that can perform all sorts of functions, but that maybe don't require the same level of control as you might have in a 6-axis robotic arm, for example. It opens up different sorts of tasks, and it just brings into the fore all sorts of interesting questions about what robotics are, what they're useful for, how we build them, what the architectures look like, and also challenges some of the assumptions about nature. There's a number of really interesting things that are happening in this space, in the sort of intersection between the world of built things and the world that builds itself. There's stuff from Marcus Buehler, looking at materiomics, this sort of intersection between living and non-living systems. The work from Mike Levin on xenobots, which is really, really interesting, and really starts to look at the sort of refactoring of life and how you can build complex organisms. So things about how do you make robots think. I think one of the propositions is that smart robots need intelligent materials. I think another one that's really sort of coming to the fore at the moment is this idea that physical intelligence is as important as artificial intelligence in embodied systems. And that's not just in soft robotic systems, it's in robots as a whole. It's about this sort of design for interaction, the physical intelligence of what the system looks like and how it interacts with the environment is what can either drive movement or drive the sort of interaction between the system that we've built and the world that interfaces with it. The point about making responsive systems from well-engineered stable subassemblies is about this idea that when you can make responsive and stable subassemblies, then you can design for emergence. And when you scale the granularity and you make more and more complex systems, then you can start to see behaviors that you didn't explicitly design. And for me, that's one of the things that we found very, very interesting about soft robotics is that when you built the system, you didn't know exactly what it was going to do until you tested it. Whereas in classical robotics with rigid body assumptions and revolute joint, etc., you know what the system's going to do when you design it. And I think that's one of the interesting things about soft robotics as a field, is this sort of intersection between science and engineering. And I think this sort of idea about refactoring biology is a huge sort of scope for interesting research in the near future. So with all of that in mind, I think basically the point that I'm trying to make is that the future is hybrids. We started looking at some hybrid work, 7 or 8 years ago now. And I think that really what we've done with soft robotics, if you think about it in the context of robots, is it we've increased the palette of technologies that are available for robotics engineers to engineer with. And that this diagram showing the emergence of soft systems from robotics actually feeds back in a nice circle where hybrids are going to be one of the things that really adds value back to robots. And so this sort of paradigm of control means that we can build upon all of the best things that we have for control in rigid-bodied robotic systems, but also bring in all these new elements and new design architectures that come from looking at some of our soft systems. So with that, I'll finish up. Few links to funders, etc., and work that's been done, a lot of it by my research group in Edinburgh.
Adam, thank you very much for this impressive talk. We have one question or comment from Marc Demelier. He says, Adam presents two systems modeling methods, lumped element modeling and bond graph. Why bond graph seems to be preferred? Lumped element modeling allows the creation of electrical equivalent circuits and can use power of the VLSI modeling tools. So do you want to comment on that?
Yeah, so the bond graph method is about our way of designing the system. So a way of sort of decomposing the system so that we can understand the energy-based interactions that are going on. So one of the real reasons why we do the sort of bond graph approach is because we explicitly model the interaction with the environment. So it's a sort of two-way port-based model which looks at the interaction of the system with the environment and the way that that feeds back through it. So it's not about sort of just taking the abstraction for the control, but it's also about how we design the mechanics of the system directly with the control and with the architecture for interaction. So, there's ways that you can use that sort of insight to feed into using tools like Simulink, for example, which is much more about the mechanics than it is about the control aspects of it. So it's really about providing insight into the similarities and differences between some of these architectures.
Thank you very much. And I think due to time, we will give the main discussion then afterwards in the plenary talk, and talk about there a bit also why robots are not so complex, as you said, and what is the future. Also, these hybrid systems are quite interesting. But now I would like to ask Professor Connor Walsh to share his screen. Connor Walsh is a professor for engineering and applied sciences at the Harvard School of Engineering and Applied Sciences, and also an associate faculty member of the Weiss Institute on Biologic-Inspired Engineering and adjunct associate professor in the Department of Physical Therapy and Athletic Training at Boston University. And also he is a co-founder of the Soft Robotic Toolkit that serves as a platform for lab extensive STEM outreach activities. And he's going to talk to you about answering the question how to educate with soft robotics. So Connor, thank you very much that you're here, and the floor is yours.
Yeah, thanks, Falk, and thanks for the invitation to present at this workshop. So I'm going to talk, about things that are probably a lot simpler, compared to many of the topics that were discussed, in the workshops today. And it's certainly nice to kind of follow after Adam, and Rob and others who have presented on, soft robotics, to kind of give an overview of that field and the potential for it. So, we've been doing a lot of work in our group trying to think about how do we leverage kind of the research that both we're doing and other colleagues, at Harvard and around the world are doing to kind of encourage kind of young people to kind of get involved in science, engineering, and math. And in particular, that could be kind of high school students, or maybe it's undergraduate students who want to start working on hands-on design projects. And we think soft robotics is a really exciting way for people to kind of get engaged in these fields and topics. So our own research group is fairly applied. So we work on a lot of applications for soft robotics. So we've worked on a number of inflatable systems or motor cable driven systems. This video is just giving the kind of simple idea of how you could use these to assist a limb. So, by having these structures, integrated into a wearable device, you can have them inflate and be able to kind of support, an arm to be raised. And that could be useful for an impaired person who's lost the ability to move their arm, or it could be for a person working in an occupational role where we want to kind of take the strain off their body so that they kind of have a reduced risk of injury. And for a lot of these systems, another reason why we think it's important from an educational perspective or has potential is that it opens up a range of different opportunities and for maybe a more diverse set of students to kind of get involved. So, certainly traditionally with robotics, it's always kind of, robots, on their own. But as Adam mentioned, I think the potential for soft robotics is where there's really interaction with people. And I think that, either for medical applications or other applications, kind of makes more people kind of be interested in the topic of robotics more broadly. And so I think that kind of is a positive. And then I think it's also quite accessible. So for people to be able to get started in this, you don't need a lot of, complex equipment. And you can really kind of get started with kind of like a very low budget and get started very quickly and be developing kind of very sophisticated and interesting things. So we think for those two reasons, it has a lot of potential. We also, do a lot of testing with individuals. So we do a lot of human subjects testing. So this is just one example, just kind of giving an overview of the potential in terms of wearable devices. So this is an individual with a spinal cord injury. And here you can see kind of wearing an inflatable device that can be very simply controlled. You're not worried about harming or hurting the person, but it's able to provide additional strength to go along with that person's residual strength to allow them to do something that they wouldn't normally be able to do on their own. And then apart from medical applications, we also think that, applications for augmenting the performance of healthy individuals is interesting. So we have a back kind of exosuit that was developed by team members in the lab that takes the strain off people who are working in industry. And so this is actually now, there's a startup company for this, and it's being worn by workers in the real world. So I'm just including this at the start to kind of mention that even though there's still, we're at the very early stages of the soft robotics field, I think already we're starting to see lots of exciting applications where this technology can actually be really practical and useful in the real world as well. But I'll take a bit of a step back and focus most of this talk on the educational side, and it'll be fairly simple in terms of its content. And really, I'll just give a perspective of kind of what we've done, over the last, 7 or 8 years or so, as we've thought about leveraging soft robotics for the purpose of outreach and education. So, a lot of, and this is maybe cherry picking a little bit, but a lot of kind of, robotics and education hasn't changed that much. People are still, selling and using kind of pretty traditional, mechanical systems where you're assembling all these discrete parts together. So they kind of come prefabricated, and then the goal of a student or an educator is kind of working on putting these together. And then there's some creativity, enabled, but certainly the disciplines are fairly limited, and the amount of kind of creativity or potential is also a little bit constrained as well. And a big thing that we noticed early on was that there was kind of a lack of like materials and manufacturing, oftentimes associated with kind of these STEM kind of robotic kits as well. And really that was kind of something that we thought, it could be interesting to leverage, for new kind of soft robotic STEM kits. So this is kind of like, why using soft robotics in education. I touched on some of these already, but it does emphasize materials and manufacturing, I think much more than, kind of prior kind of soft robotics or prior robotics educational materials. And I think inherently there needs to be a fair amount of kind of creativity and, put into, kind of designing and fabricating these systems. And so I think it kind of is exciting to kind of students, and they really kind of have, this kind of infinite set of possibilities about what they would be able to do. And so I think that's important just in terms of kind of training people and to be better designers and innovators. And then, we think that it can be quite accessible. Like I kind of mentioned, that already. So these are just some pictures kind of some students who would have been working in workshops on soft robotics. And then beyond, kind of high school students, we also think that, there's an opportunity in research. There's a number of research groups here today presenting that focus on soft robotics, but oftentimes, because this field is relatively new, if there's a research group that doesn't have experience in this area and wants to get involved, how do we kind of like create pathways for them to kind of quickly get up to speed and start working on their own soft robotic systems, even if they haven't had that prior experience or domain knowledge. There's no real textbook you can buy on this stuff. A lot of the material has been developed over the last decade. The field's moving quite quickly. So kind of how do we create platforms for kind of enabling researchers to kind of get started? That was kind of another thought we had early on in this project. So that really led to kind of the development of the Soft Robotics Toolkit. And I think we started this in 2014. So, there's Donald Holland played a big role in this as part of his PhD. But basically we wanted to develop an online portal that kind of helped collect a lot of the information from the field and to make it, sharing across different groups and maybe helping others be able to get started in this area if they didn't have experience in it. And so you can go to softroboticstoolkit.com. I think we're okay, but maybe not great at keeping the website updated, but there's a lot of great content on there. And really kind of, we've had a lot of interest from, in the broad community. So makers and hobbyists, we get emails from people just looking to kind of get started in soft robotics. We've run some competitions, which I'll talk a little bit about. So we've had kind of high school students, undergraduates, and also graduate student researchers kind of leverage some of the content that's been put on there. So it's been quite successful, I would say. So, we've had, over 3 million page views and, many different labs that have contributed content on here. So, it's really kind of, we're kind of curating kind of like a lot of materials from the field and trying to kind of organize it and put it here. And we kind of provided a framework for how to do that, but it was really groups, putting in some time and effort to kind of share that content that has enabled this to be successful, and then have really kind of had broad impact. So, really enable people all over the world to be able to kind of get involved and get started in this field. And still, I think, have an average of 300 or 350 visits a day. So there's still like a fair amount of people leveraging and using content on the website. And so when we started, we put together content on the website, and then, ourselves individually, we wanted to think about how we would run, workshops and start working more with students and also working more with educators. So over the years, we've run a bunch of different, outreach activities. And with kind of very young high school students, with students kind of at, maybe kind of like an undergraduate level. And we've kind of run workshops with educators where we try and train educators on this and get their feedback on how they incorporate this into the classroom or into extracurricular activities that they would run as well. And we've kind of done this both in the US, and we've also tried to kind of, go a little bit broader than that. And so we've done workshops in Peru and India. And I think that's really where I think there's the potential for impact, because, oftentimes the cost and affordability of some of these kind of educational materials is really critical and important to them being accessible. And so I think, we've had, a lot of interest from people there in terms of how they might kind of deploy that. And I would say in Peru in particular, I think there's, some faculty there that have continued some of this work and kind of are still running workshops, locally there. Based on collaborations that we've had, over the years. And then I think, the content on the website itself. So if you go through the website and have a look, we kind of have, material that's been shared by different research groups. So that's kind of like maybe the most hardcore part of it. So, really kind of what, someone might be doing as part of their PhD research or postdoc work, people are sharing on there. But then we have a bunch of different projects for kind of getting started as well, because we realized that maybe some of the material that was added was a little bit inaccessible to educators if they wanted to use this in their classroom, or even kind of students. So we really tried to think about how do we kind of start to break it down into more bite-sized activities and have kind of like easy to follow lessons that we can put online with some supporting materials and activities that people would be able to use in their own classroom. So that was kind of like where we started in terms of kind of developing these kits. But obviously a person still had to acquire all the materials themselves. But they could follow all the instructions, that we had provided. Additionally, we've tried to put together case studies on there. So, this maybe isn't super up to date, but because there's been a lot of new exciting work kind of with demonstrations and applications, but some projects that kind of highlight kind of like what's the potential for soft robotics to try and inspire people and to potentially think about other applications. And then the competitions, I think, was a very exciting aspect that we ran, and many people in the field volunteered their times as judges to kind of judge kind of the submissions. But we had a high school level, an undergraduate level, and then a graduate level competitions. And I think almost 1,000 students actually, participated in various different types of competitions where, we either got them to upload some exciting new material based on some, advances in their research if they were a graduate student, or if they were a high school student or an undergraduate student, we kind of got them to demonstrate something cool, with the kind of content and material that was accessible kind of on the website as well. So this was a way to also generate more content for the website. So, by participating in the competition, you had to upload your work, and then that becomes accessible to other people. So it was also meant as a way of kind of continuing to kind of encourage sharing amongst the community for all of these different projects. But then one question we had about 2016 was, as we were kind of in these competitions, was, we were hearing from people that, they still had a challenge in kind of getting started. So they had to source the material, find all the tools. And so even for some educators, there was this kind of barrier or perceived barrier to kind of getting started where, we were thinking about how would we make this even easier for people to get started. So that's kind of where the idea of thinking about, could we actually start to develop some pre-packaged physical kits that people would be able to use to get started. And so, we've gone through that exercise, for one kit. So we have this soft robotic gripper kit, which I'll talk a little bit about. And then we'd like to use those introductory kits for people to kind of, build something specific, but then be able to have exploration kits where maybe they would leverage all those materials to do something new and exciting that would be building off what they have learned. So we developed this kind of pretty cool soft robotic gripper that you can kind of see here that has some material casting aspects to it, some mechanics, some electronics, a little bit of programming. And then we started to kind of run workshops with it where we would kind of get feedback and understand which parts worked well for students or educators, which parts kind of could change. So we've actually run a real bunch of studies in the US and in Europe, and continuing to iterate and refine the device. So here's kind of what you can see as kind of like the final version now. So, it comes with a bit of, parts, some components that you do have to assemble, but then there is also this materials and manufacturing element that is maybe a little bit light, but kind of introduces people to kind of getting started in those topics. And then for the exploration kit, we provide more materials and some other tools that allow students to kind of build off what they've done already. So this is kind of the introductory module. It can start very basic. You just, make some soft actuators and you actuate it by pulling on a string. You can then kind of add in some, motors or sensors as well. And then you can also kind of, have it kind of detect objects automatically and be able to close, based on that signal. So adding in a little bit of logic and programming there as well. And then after they go through and build that, then we say, design a gripper for some other exciting application. And so maybe this isn't quite as sophisticated as what they're, doing, building the introductory kit, but still they're able to kind of go through this process of thinking about maybe different geometries, different designs, different materials. And really this is where they get to kind of exert their creativity and be able to kind of build something, based on their own ideas, and rather than just something that we're asking them, to build directly as well. And so we're excited about this idea of introductory modules and exploratory modules. And then recently we've been running some pilots. So because of the pandemic, we had to think about how we run workshops virtually. And so we started this with, collaboration with Holly Galecki at UIUC. And so basically kind of, they have an after school program and with some high school students. So we trained an educator and then we ran this where we provided materials to every student's home, and they went through this virtually and kind of were able to all build, a version of the gripper that you can see here. And we also ran a bigger pilot in India, and we had a collaboration with Tata Trust there, where we sent this to kind of, I think it was 6 different schools. So we had a workshop over 40 hours where we trained the teachers, and then the teachers ran this workshops with their students doing this at home. And so we really like the idea of this model, train the educator in these materials, have them gain confidence in it, and then, make the materials accessible and affordable enough so then people could do this in a classroom or in their home as well in the future as well. And so, you know, the other thing that we recognize is that beyond high school students, you know, we do want to think about how would we enable the research community to get started. So this is just a control board that, you know, a former postdoc Panis built back in 2014 that we just put online and said, here's how you build a simple control board. And, you know, many different, you know, people just built this themselves off the design. So it was exciting to see many research groups leverage this. And I think as former Harvard students started a company and started selling these, you know, at cost. And I think Facebook or Oculus actually bought some of them. So that was kind of pretty cool as well. But we definitely recognized that this wasn't very sophisticated and it was really just a first pass. So more recently, we've been trying to think about how we might make, you know, a more sophisticated version of that control box that we could kind of share with the community, so that people would be able to kind of maybe, you know, perform kind of like more sophisticated or complicated things, maybe do more sophisticated programming, and maybe have a greater number of degrees of freedom, and have it be more compact, maybe have it be portable or wearable. And so this is kind of something that we hope to release sometime soon. But it's been an ongoing effort by a bunch of people in the lab, kind of trying to, you know, make something that isn't so tiny, but still, you know, is quite portable. And we'll have some instructions to kind of go along with it as well. And then we've piloted this already in a class that, you know, I teach, a graduate class. So, you know, in addition to the control box, we also kind of have some introductory labs. So kind of making kind of the new net actuators that, you know, Adam showed and Rob showed, and then also kind of different types of sensors or actuators, and to allow people to get started. And then it's exciting to see that, you know, very quickly, you know, someone with no experience in soft robotics is able to kind of get started, make their own actuator, connect it to a sensor, connect it to the box and get it to move. And that's really when people start to think, oh, what could I do with this? You know, so it's kind of lowering that barrier to entry of kind of getting started in the field. And then, you know, beyond just kind of making actuators move, people can start to think about cool applications. So here you can kind of just see one team, we're thinking about how do you make a wearable mechanotherapy device using this platform, and they were able to kind of get started very quickly and maybe iterate, you know, much faster than they would be able to if they have to start from scratch themselves. So I'm going to stop there and just kind of acknowledge that there's been a lot of people. We're partnering with some, you know, other groups that are giving us very helpful feedback. A lot of lab members have contributed to this, Donal Holland and Holly Galecki, you know, more specifically to some of the research aspects. And then many people, I just thank, you know, Rob and Adam have been great, and then others in the field and contributing ideas and content from, you know, their students or others and helping to be judges for the competition. So it's been a really nice effort to kind of see the community get engaged together in this. So thanks.
Thank you, Connor. That was a great talk. And we have actually a few questions. First one from me would be, where can I buy this? And do you ship to Europe?
Yeah, so we have some team members in the lab, and one person, Alex, who's leading this project currently. And I think there's definitely some motivation to try and think about how we would make it more accessible. Mm-hmm. I don't think we quite have a plan for that yet, but it's definitely something that the team is interested in. And in the meantime, I guess if you think something would be helpful, you know, we're happy to just kind of get started. And so we could be in touch after this. And I would open that to anyone. You know, we're happy to just be in touch with people and start collaborations. But longer term, we would like to figure out, is there a way to kind of actually have people be able to purchase this? But I don't think we're quite there yet.
Mm-hmm. Cool. Thank you very much. Yes, I would love to buy one of those pumps, actually. And we have a few questions from the audience, actually. First ones would be from Vicky Voluzzi. Do you have any specific educational methods when you present the material? I think you also directly answered that with your talk a bit. And have you noticed any gender age differences in the students, how they approach the material or competitions?
Yeah, that's a good question. So for the latter part of the question, I don't think we've really seen any big differences. I think, you know, we've definitely had pretty diverse kind of groups of students who have participated, you know, in terms of gender and age, and also kind of, you know, background and economic background. And so I would say so far, at least, we're not really seeing anything that jumps out as like some people being more excited or some people being less excited. And I think that kind of matches our initial hypothesis that we think, you know, maybe with traditional robotic systems, it may be more appealing to kind of certain individuals rather than others. But so far, we've seen kind of pretty broad interest and participation.
Yeah, cool. Thanks for this answer. And Xiao Sheng asked and said, thank you for the presentation. I have a question about the soft robotics education. Do you think how the students should get started in systematic understanding of software robotics like a university course, so they can have essential knowledge to further do research in the relative fields?
Yeah, so I think what we're doing is maybe like a step below that. We're really focused on how do we help people start prototyping with software robotics, I would say, is probably where our focus has been. When it comes to kind of maybe courses, you know, at the either undergraduate or graduate level, introducing, you know, a lot of the kind of concepts, the more fundamental concepts. Yeah, I think that's a great question. I don't think we have taught too much about that. And I think that, you know, some of the material that Adam just presented and, you know, or others, I think it's a very diverse field with many different types of disciplines and expertise. So I think it would be an interesting exercise to think about how would you design, you know, a introduction to soft robotics kind of university level course. And maybe some people have already done that, and I'm maybe just not aware of that. That's probably the case. So I'd also kind of defer to maybe other people in the field if anyone else has started to do that. But we haven't tried to do that explicitly yet ourselves.
Okay, cool. We have two more comments, one from Karen Donaldson. The toolkit concepts and workshops are excellent. This work of the team should be congratulated on. So congratulations on the great work. And also it's very inspiring, your talk. And one person from Iran says that it appears that they cannot actually access the soft robotics website using VPN. And if there was a possibility to actually get access to this website from, for example, Iran.
Yeah, if people want to send me an email with those questions, like I'm happy to see what we can do. I don't know exactly if I'm technically competent enough to figure that out, but you know, it is hosted on a Harvard server, so I'd assume that it's relatively accessible.
Okay, cool. And I would like to thank you really much for your great talk and also for the toolkit, because I also used some of your ideas and solutions in my PhD, and we're still using some of those in our projects now. And I think it's a great contribution to this field. And with that, I would close now the session and would open the plenary discussion on the future of the field, actually. And just to get this started again, I would like to share my screen again, because we have a few questions that I would like to answer or ask everybody here is what's next in the field of soft robotics. So we saw a lot of talks today. So we saw that it would be embodied energy, embodied intelligence, new fields of 3D printing, 4D printing actually, and also the quite interesting STEM research here. And I want just to ask you guys, would be the next in the field of soft robotics here? What do you think, and what's your opinion on that? And actually, yeah. So Mark, Adam, Robert, and the other speakers of today, what is your thought on what's the next big thing, or what would be the next great challenge that we all in the field of soft robotics should attempt to tackle here? I
think I covered it a bit in my talk, but as with all good science, then science fiction got there first. So I think the liquid metal Terminator from Terminator 2 is the next big thing you're going to see.
Yeah, but only with your embodied intelligence and Robert's embodied energy.
That's right. It needs all of those things.
Yeah. Yes.
But I mean, seriously, things like that are about sort of reconfigurability and about ways that you can design resilient systems and sort of blur the lines between the world of made things and the world of things that makes themselves. Really
Adam, I just got a message. Could you try to speak up a bit, because you're a bit quiet?
Yeah, sorry. I don't know whether I'm just too far away from my microphone. It's my thing. Can you hear me now?
Okay.
Yeah. You can always hear people when they say, "Can you hear me?" So anyway, I'm not sure it was interesting anyway.
I think it was quite interesting. So, so what is the other guy's opinion on what's the next big thing, and what's actually also the next one of the big challenges that we could tackle over the next 5 years? Because I think one of the challenges would be to have really materials that could multi-material systems and smart material systems that are actually able to gather energy from the environment, adapt to that, and also sense the environment, that all in one material here actually, or in a system, multi-material system.
I see that Mark's unmuted, so maybe are you going to say something, Mark?
Yes, if you look at natural systems, either plant or animal, there's something which strikes me, and that was alluded to by Adam when he was mentioning Marcus Buehler with the materiomics, is the various levels of hierarchical functions you have, up to 7, for example, for the bamboo, or 4 for the bone. And what you have at each level, you have this kind of holy trinity, I will call it, between process, structure, and material properties, and you provide information then to the next level of hierarchical function. It'd be nice to be able to get smart materials which allows you to have this embedded information going from one level to another, and to see. As a way, for example, of self-adaptation and self-healing, etc., that would be quite smart to be able to see that in biorobotic system. It starts happening. It'd be nice to have it at higher level, or many different type of levels. But that's my dream for the next 10 years, I would think.
But would you say we need to start at the smallest cell? So if we think of it on a unit cell level, or
No, not necessarily a folk. It doesn't need to be that low. I just, it'd be nice, for example, if to see a robot, for example, retrieving his or her hands from a very hot surface, for example, because otherwise it would melt the silicone, or it would melt the rubber, or the hydrogel. Without necessarily having a central intelligence information relayed to the central unit, because that's the way humans are acting upon. They are not. You act much quicker than what than an activation by your brain to retrieve the hand. So having this kind of I would say even human-like behavior would be quite nice to have in terms of immediate reaction. So that would be nice to have. So that would be one aspect of it. And the other aspect, and that was alluded by Robert, is the ability to have storage of energy or creation of energy locally as well. That would be quite nice to have. Okay.
On the material side of things, I think the membranes doing more work than just mechanical work. Electrochemistry can be done quite well in hydrogels, and so there'll be a lot of sensing and synthesis and even computation that can be done in the skin itself. So I think that's one of the things I'm excited to work on.
But do you mean only on chemistry level computation, or also on a mechanical level?
Well, you could. I'm not doing this work, but several people are in the BZ reactions for oscillatory reactions for clocks and things like that. But that's not what I'm talking about. I mean a chemical amplification of a stimulus, which could then result in something that Mark was talking about in reflex actions. So in that case, it would be a chemical input to a mechanical output. But the thing that we're actually working on is to harvest energy from the environment through hydrogel membranes, through electrochemistry. Okay,
cool. But that would be also coupled with the logic system of Adam, right? Because he uses, or he showed us some pneumatic logic systems there, right?
I presume, yeah, I presume that there's a lot of value in not doing things with silicon systems. But because we don't work in the fluidic logic world, and there are much better people like Adam doing that, we're just gonna couple the amplification, electrically amplified signals to an MCU, and then output the response into these microgear motors, because I think there's so much to do and it's so hard to do these things that adding another research topic on to it would be too difficult. So we hope that what we show with these chemically amplifying skins, that other people see that it's translatable to other systems, and then they can do that if the value's there. But one of the things Adam was saying is everybody's doing subsystems and layers of subsystems, and a problem with that is what I proposed, where I'm going to work on this and show that it works. It's not as easy to get somebody to adopt it and incorporate it into their system. So one of the things I really liked about Adam's talk was these transformations as a way to not necessarily have to do the research on your own, but to be able to predict how it would be integrated together.
Yeah, no, I think as a way of taking that and mixing it with comments from Mark and Rob and Connor here, one of the aims with some of the tools that we're trying to develop is to build upon the sort of thing that Connor is doing with the Soft Robotics Toolkit, but in a way that is not simply about sharing pre-existing designs, but it takes the sort of information that comes from those designs and allows people to think about creating novel designs. Because Rob is a very skilled designer, right? Comes up with good designs, makes things, which is great. But one of the issues with sort of making complex systems is the ability for people to design complex systems. If you feed in the design requirements to it, then it relies upon the skill of the designer and the knowledge of the designer to be able to make that thing. And so one of the things that Mark and I were talking about a little bit in the sidebar chat there about the VLSI approach to doing this is about sort of putting in behavioral level requirements and then developing a system that will do synthesis, right, of the design. So instead of having skilled designers with their tacit knowledge and their understanding, then you feed it into a software package and it pops out the design, right? You don't know how it works, you don't care, it just does what it does, right? And I think that's a really interesting field of research that we're moving into. We're doing a lot of work in that in hydraulics at the moment with a spin-off company that we've got together. But doing that with a range of other technologies and increasing the complexity is a really, really interesting area of research, I think.
So you think one of the things that will be in the next 10 years will be just a software where we have to say, okay, my soft robot should grab that, and how can I build that, and just will pop out these systems? Because actually we are also working in some kind of living, adaptive, and energy autonomous systems here in our cluster, and that is one goal that we actually also have to provide afterwards is tool that people can say, okay, I want to use this unit cell actuator or this pneumatic actuator, and say, okay, just give me the software, and I put it in there and say, okay, I want to have that gripper take this part here from A to B, and then we have this nice system here. And yeah, there's also one question that I would say after Mark's comment on that would be also, do we go back from pneumatic systems actually to have something that is really shifting to purely electronic driven systems? Because I think if we have solar powered robots that drive electrorestrictive materials, that we would gather a new kind of area there where we can say, okay, we want to have soft material that can be actually actuated via solar cells, flexible solar cells or something that are integrated actually into the system there, and go away from this pneumatic system. Because I think pneumatic systems are great, but they have their backfalls because they need this fluidics or pneumatic.
Well, I know that Nathan Lepora is on the call here. I examined PhD from Michael Dicker at Bristol a few years ago, where he built some amazing photoresponsive hydrogel materials, which were brilliant. You know, sun tracking systems that would change the mechanical response of the system in response to light and things. And for me, that's a sort of really interesting thing that ties into stuff that Rob was saying there about how you can make systems that, you know, are, they don't have electronics in them, they don't have centralized control. It's a sort of embodiment of the mechanics and the, you know, the physics, the chemistry, the all of that sort of redox stuff that goes on. It's really, really interesting stuff. So I think there's a number of really interesting things there.
Mark, you wanted to wait?
Yeah. Just to answer your first concerning software, shall we have, and also an indirect answer to Vicky as well. I mean, being relatively established researcher, that is in bracket old, I think it's very interesting to see what has been the evolution for VLSI design and also for microelectromechanical system design software. And it has been the same. There has been a plethora of various software created independently by people. Then there was a serious industrial intake, and they have been choosing, and as a consequence of it, companies have been interested to pick up what the research did. And then you had what we call aggregation of software, consolidation of the various software into a platform. And I've seen that happening with VLSI design. Now you have Cadence doing that, maybe a little bit of mental graphics in the past. And for microelectromechanical systems, you find exactly the same thing. We used to have IntelliSense, we used to have various other name of software companies, which I forgot the name, but now you have two main players. You have the console suite, which is I call it quick and dirty. They will not like what I said, so please delete the record. But there is, and then you have the ANSOC, the HFSS, you know, the ANSYS of this world, which is being used for MEMS devices. In biomimetics, you find exactly the same. You have 54 tools, 17 are decent. They try to do, they're all over the place. But at some point, you will have a conversion of software, and you will have a company which will believe that there is a real value into creating software a little bit more professional. So to come back to your original question, would that be something in 10 years' time? It will depend on the industrial intake. It's very much so. And the companies who are creating this kind of modeling software could be in for the big bucks when you have the big players such as Cadence wanted to acquire their software. So this is a way it tends to work really in that field, in my view. Okay.
Okay, thank you on the comment. Yes.
Maybe just one last kind of comment, just related to kind of like applications. I think, you know, we obviously do a lot where we're interfacing software robots to people with wearable systems, but there's a lot of challenges with that. So I think kind of new approaches to, you know, kind of overall design or manufacture of these systems that enable a more intimate coupling between kind of like the soft robotic systems and the people, I think is kind of certainly something that remains kind of like a challenge. You know, and doing that from the outside of the body, you know, you have to interface, you know, with all this kind of soft squishy material. So that has unique challenges. And then I think even more so, I think it would be exciting to think about, you know, more and more implantable applications for kind of soft robotic systems as well, where maybe kind of some of the capabilities kind of like mean that maybe they're more suitable for long-term implantation. Maybe they can biodegrade over time. I think there's kind of a lot of interesting kind of like potential there on the medical side that probably hasn't been fully explored yet as well.
Yes, I completely agree. And I know that there is also some tattoo-like soft sensors already there, right, in the field. And if I remember quite good, the soft sensor, wireless sensing of Mark's capsule there, where you try to porcupine peristalsis, was also quite interesting. Yeah. Yes. But one question to that, you really have developed a tetherless, so wireless sensing system there, right? So the only thing that I quite remember from our test with our system our pneumatic artificial gut system that we developed and you used was that the tether was just to bring it in the system, but you don't need it actually to get the sensors.
Yes, it doesn't need to be tethered. You know, you have enough battery life to do that. Coming back to what the great work that Connor has done, I mean, I cannot help linking it to what has been happening in the UK and then slightly more abroad with the Raspberry Pi, which has been an electronic platform, which has created a huge interest among the young generation into coding and into looking at application involved in coding. And I think what Connor is doing is actually quite important because it brings really the soft robotics technology to the masses, to the people, to the education, and try also to demystify what soft robotic is, and also allow to create a positive image of what the technology can provide. And I think it's a very important work. I believe that's what Connor is trying to do, and I applaud him for that.
I would say, you know, Alex in the lab, who's like interested in trying to figure out how this might kind of go outside of Harvard at some point. Oftentimes when he's talking to people, the response he gets is like, why should anyone care about soft robotics? That's definitely kind of like one of the things. So I definitely think it's something that isn't really well known. I think it's still a very disparate concept to a lot of people. So I think kind of, you know, just, you know, broadening kind of, you know, the message on what's possible with that, I think is important because a lot of people still look at it as like, you know, why is it important? And, you know, when you think about it for education, like why use this? And so there's a lot of people who aren't familiar with soft robotics.
I think that is one of the great 5 challenges for the next year, to get people to know soft robotics here. So we talked today about the field's future, and to get back a bit on this, where will we be in 10 years? What do you expect, except from the Terminator there? But so to pinpoint it a bit, will we be really seeing autonomous systems there using energy from the environment, driving actuators, grippers, that can actually really react to something that they're gonna grip or that they want to grip actually? So will we really see in 10 years a self-conscious gripper that says, okay, I want to grip that because that is my job right now here? Or are we still too far away from this? What is your guys' opinion on that?
I think if we want grippers, then we'll have grippers in 10 years' time. But the question is really, who actually wants soft robotics? What's it useful for? You know, the thing that drove the VLSI revolution was consumer demand, right? So I think if you look at the way that robotics as a whole is progressing, then it's pretty safe bet to say maybe in a little bit more than 10 years, maybe 20 years, robots will be around us in the same way as mobile phones are, but in such a way that we don't really notice that they're there, right? When mobile phones first came out, you could see them, they were a big deal. I think robotics will become a sort of ubiquitous technology that will disappear into the background. And I think one of the things that will enable that is soft robotics. So I think probably the question about what will soft robotics look like in 10 years' time is probably another way to phrase that is, what will robotics look like in 10 years' time? And I think the answer is soft robotics.
Yeah, that is a great opinion, yes. Mark?
I will have two answers for that. The first one is we do not know what application will be the killer applications, and we might be very surprised by it. I mean, for example, smartphone, the text messaging in smartphone were not used primarily for one teenager texting his potential girlfriend across the dance floor. It was used for engineer to try to basically troubleshooting the mobile phone. So we don't know what the application is. But if I was taking nevertheless a safe bet, and that's my second answer, is I would look at the needs which are not being met at the moment. So one of my jobs is to create medical devices, and the best way to start is to look at what the clinicians are needing in order to what are the needs which haven't been satisfied yet with current technologies. So that's usually a very good start. But it doesn't mean, as I said, that the application will be one which satisfies that need. And again, I come back to my first answer.
Okay. Robert, do you have an opinion on that?
I think early success in commercialization is what will help make a more accurate prediction of the future. And there's an example of a company that failed called Empire Robotics, and they were making an adaptive gripper based on jamming. And then there's an example of an adaptive gripper based on pneumatics that so far has been, well, it's been much more successful than Empire Robotics in terms of fundraising and demonstrated and paying customers. And the fundamental abilities of both, I don't know if they're all that dramatically different for what, but one was successful and one wasn't. It could be that Empire Robotics was too early. It could be there wasn't a reliability issue there. I'm not sure. There's a nice paper on it though. I think John Emmons' hypothesis was that it was early, and maybe Soft Robotics Incorporated came around just in time, and it does seem to be working. So I'd say logistical and supply chain operations, pick and place in an Amazon warehouse, and agriculture, I think, is going to be a big opportunity for harvesting fruits and monitoring, doing phenotyping of different genotypes automatically. Underwater exploration seems to be a technologically robust place for us to be doing our research. It works pretty well right away. So whether or not the need is there, the ease of doing it is there, and will probably more rapidly arrive I think Adam has a company, something to do with the ocean. So maybe that'll work out. And sensing of things like soft sensors, I think for us, I have a company making soft wearable sensors and sensing skins for robots. And there appears to be some real advantages for that too. So I think tactile perception, agriculture, haptics in wearables, underwater robots, I think we'll see our presence there in 10 years.
Thank you.
I mean, one thing to pick up on what Rob's saying there, which is quite interesting, I think, is this sort of the role of entrepreneurship in academic research, right? Because, if we talk about how things get out of the lab and into the market where they get tested by customers, the only way to do that is to get them out of the lab, right? And that's a really difficult thing, actually, getting stuff out of the lab and into the real world. But it's rewarding when it works, and it's useful because it gives you actual feedback. I think all too often academics are guilty of living in a bubble where they believe that their inventions are interesting and useful. Sometimes they're interesting, very rarely they're useful. So,
yeah, it's like we should all try to be in the Pasteur quadrant. Not all of us. I mean, some of us much smarter than me are able to be in the Bohr quadrant, but I'm just trying not to be in the Edison one. But I think, I think that's what we should be doing in the soft robotics community, is trying to stay in that area of the quadrant and try to be thinking, is this ultimately useful? Because there aren't many of us making new laser beams, new forms, but there is a lot of real important engineering to be done, and some scientific discovery too. So I don't think we have to think 100 years into the future. I think 10 years is I think that was a really good timeline for.
Thank you for that comment. And I think now is a perfect time to end because now we're actually at the end of the plenary discussion. And I really thank you all for participating today. It was a great workshop. We had great new insights, learned a lot. And planetary discussion shows that the field is still growing and will be growing in the next few years. We have a few really interesting challenges ahead. And if we want to change the world, then we need to bring them out there, actually. And I thank you all very much. I hope you enjoyed this workshop as I did and the great talks today. And please keep in mind, tomorrow at the same time, we will start the other workshops. And actually, you can also hear something about my current research because I'm giving a talk at the Plant by Inspired Robotics. So feel free to join us the next few days. And thank you very much to everyone and have a good day. Bye-bye.
Thank you very much. Bye-bye.
Thank you, Volk. Thank you.